let's make a little bit of a list here so we can stay on target. There are so many features of this game, and we really want to get to gameplay at some point. What we know is that we need to get our update loop to deal with time. So we want to calculate delta time, which is dt. And again, that's the time since the last time we updated. So time since the last frame, rather. We want to be able to update all entities with the dt, so they can use that in their internal calculations for movements and physics and collision detection and anything else that might require a sense of time. We want to also perhaps provide them with controllers. We want to be able to give some user input. So let's add that. We want to add and remove entities. I'm just writing this here so I don't forget it again. We have to call add and remove entities at the end of every frame to clear up our entities list as needed. Then we need to render. And rendering right now is calling render on the entity, passing in canvas and paint. The static entity is calculating, right, okay. So this needs to be a little bit more complicated. At the moment, we are assuming that the entire game world is in view the entire time. And when that's true, when the game world and the screen size match, this logic will work. We just take the in-game position and translate it to the screen. But if you have a camera that you want to view the game world through, the camera might move, which means your entity moves relative to the camera. It remains at the same position in the game world, but where it's placed on screen is up to the camera to control. If you open module number, let's see, week 5, we have implementing a viewport, which is an article that shows you how this camera class could be implemented, and also the features you can get from it. So in this case, I've told the viewport that I want to show more height than width, and is running in portrait mode. We're fairly close to the player, and whatever position is it, blah, 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 whatever. We can also zoom out, and we can be extremely zoomed in. And in this case, again, the camera is positioned just in front of the player. But it might be the camera is way over here, which means the player would have to go to the opposite edge of that screen, retaining the same in-world position, but a very different position on screen. So that's a long and rambly way of saying that we need a viewport. And if we need a viewport, or a camera, we are going to have to ask the camera to translate our in-world position to the screen position, because it's the camera that controls the location of everything on screen. Ooh. So, okay, that means this is going to have to be slightly more complicated, but since you have that code available, you can go ahead and whip up something like this, which is the code from that article. I should just add this to the bottom of it, I think, so you can copy paste it. But if we bring this in, we create a new Kotlin class, we call it a viewport, and we paste that, we zoom in. So it takes 4 arguments: the actual resolution of our screen buffer, and then the number of meters to show on each axis. The only thing the init function does is calculate how many meters to actually show. If you pass in that you want to show 19 meters on the x-axis and 0 on the y-axis, it will calculate how big y should be to fit the screen exactly. And vice versa, you can pass in 0. So you prioritize the axis that you care about. You can lock them both, but you risk not matching the aspect ratio of your buffer. So if you end up doing that, your graphic will look squashed. It will still run and it will resample fine, but you ideally want the aspect ratio of these two to match the aspect ratio of these two. And if you provide only one of these, then the other one will be calculated to match perfectly. The logic is not difficult, but it's slightly hairy, mostly because we need to see which value was actually set. and which one do we want to calculate. So that's that. It provides functions for positioning the camera over a coordinate in the game world, an entity in the game world, or a point, because we have the point object. You also have the translation functions for, well, it's one and then a bunch that takes convenience features. This function translates, and we can do this one instead. It translates an entity position into a position on screen, taking into account the camera. So as you can see, this expression is far more involved than what the static entity is currently doing. This logic only works if the screen and the game world have the same view, so to speak. But the viewport here lets us move the view independently. Okay. Apart from world to screen. Oh yeah, one thing to notice here is world to screen does not provide a return value. Instead we pass in a point object that we use as the output parameter. And the reason for that is we have to call this function many times a frame. And we don't want to create a new point every single time we do. So instead we have one point that keeps getting reused every time we call world to screen from our update loop. Lastly, there are some tests. These are called clipping tests or clips, where we check if an entity is in view or against a rectangle if that's convenient. It's the exact same logic. This is also essentially the same logic as the current collision detection in our base entity. It's just a rectangle intersection test. So with that viewport, we can build a visible set and draw it. So build visible set, which means we have to update our render to render visible set. Let's see if we can get the viewport into this. So we start with creating a camera object of type viewport. It takes a bunch of arguments. At the moment, we are calculating our screen width. Rather, we are requesting a screen width by using set fixed size here. So our buffer will be this size if everything goes all right. Which means I should probably pre-calculate this. So if we're going to reuse it like this, let's just do stage height equals get screen height divided by 2, stage width equals get screen width divided by 2. Then we use those in here. So stage width and height, it's the different order. Let's do it this way. Stage width, stage height, and our viewport can use the same ones. So stage width, stage height, and then I want the number of meters to show. We can make those constants. So constant value, we can, yeah, that's good. Meters to show on X. Let's make that, I don't know, 20. And then const val meters to show Y equals 0, so that we let it calculate the height that's required. Meters to show X, meters to show Y. That should be our viewport in place. So using that, we need a function to build the visible set. Let's see how that would look like. Private function, build visible set. Boom, boom. That means we need an array list to begin with of our entity. So I'm going to copy. I'm just jumping over to the level manager to not have to write this code again. Go back to game and add another member. Private value. Visible entities. Right? And our render thread is going to need, sorry, our renderer, like that, array list entity, visible set. So our render is now adjusted. The render call needs to provide that as well. So visible entities, we need to call build visible set. I'm doing this in the reverse, which makes no sense at all. Okay, build visible set. In fact, let's do one more thing in reverse here. At the end of a render function, we need to make sure that we clear the visible set because we're done with them. And we no longer iterate over the level manager's entities. We only render the visible entities. So render takes an array, it loops over them and renders them and then clears it. We need to rebuild it every frame, and that's good. So now we can get into using the camera. Essentially, we do, in fact, let's do this instead. Instead of clearing it at the end of render, let's clear it before we build it. That makes more sense. So for each entity in level manager entities, so that's our entire level, if camera says that you are in view, visible entities add that entity. That is it. This should provide us with what we need to render. This should all still work. Let us test. And booty. And allow that. All right, so far there's been no changes, but it's working, so that's good to know. Nothing crashed. Let me see. We can clear out now. We're rendering a visible set. We're building a visible set. And this is good. Next up, we want to get the positioning of the entities right. We are currently, let me just see what the default positioning of that camera is. The viewport is positioned at the top left-right coordinate of the game world. And so, okay, we need to be able to ask the camera about our position. The entity does not currently have access to the camera, but we could, I was going to say, we could pass in the camera to let the entity talk directly to it, or we can move this code out entirely and pass the translated coordinates of the entity back to the entity, but that would also seem silly. So an option is to create and use a matrix transform instead of using these coordinates. So the render function, instead of taking canvas and paint, should take a canvas and a matrix and a paint object. A matrix is a useful mathematical tool where we can go back to modules here just to see what we can do with it and check the transformation matrix. It allows us to perform linear algebra. So we can do geometric math handedly without having to know any math. We can, here's a sample render function that takes a transform. We can use it to scale the bitmap. We can use it to move the bitmap by translating it. And we can use it to rotate the bitmap. You can skew the bitmap. You can do all kinds of stuff. You can check this article out, but essentially it allows us to do stuff like this. Rotation, movement, scaling is not demonstrated, but that's also available. The benefit of using a transform matrix to manipulate the pixels of our bitmap is that we no longer need to copy bitmaps all the time. If you check our bitmap utils, you can see that, I think at the bottom here, when we want to rotate a bitmap before, we would create a new bitmap. When we wanted to flip the bitmap, we are scaling it on one of the axes and then creating a new bitmap from that source. Same thing with essentially any modification we were doing before required us to create a new bitmap. But this way, using the matrix, we can flip and rotate, which means we can use the thing I was talking about, the animation frames, they're facing to the left, right? If we wanted to face the other way, we can now just use the matrix to flip the bitmap without creating a new one at all, just reusing the same frame. It's highly efficient, and I think that's the way we should go. That way we can have the render loop in our game class just set up that matrix, post it in here, and be done with it. So if I go to the entity base class, we can update the render base function to take, we can call that a transform, and it's of type matrix from the Android graphics library, not the OpenGL one. Import Android graphics, thank you. Then I'm going to grab that and go back to static entity and make sure that the override is in order. And then raw bitmap, we can simply change this to accept a transform. And that's a different version of draw bitmap with a lot more flexibility. And so again, if I go back to that article, if you can see this super tiny code here, you can trivially add the support now in your entities to have a scale or to have rotation and rotate around any point even. This is super useful stuff. And all we need to do is set that, that transform up in our game class. So we go back to our core loop. We're going to need to reuse this. I'm going to make it a member. Value, I think we can reuse the same instance. We can call this transform. It's a matrix. Can I do this instead? Import. There we go. So we have this one matrix that we keep reusing. We actually need a point, don't we? So we can, well, maybe not. No, we do. We're going to need one. So a transform and a point. We can go back to our renderer. And so for each visible entity, we have to first make sure that the transform is empty. So we do a reset on it. This means it will make no changes at all to the bitmap, right? Then we want to ask the camera to translate from world to screen using this entity and our, well, I called it a point, didn't I? That's stupid. Let's rename that. Rename, refactor, rename to position. That's an output argument, right? We don't get the return from world to screen because I want to reuse this. It's a cheap and dirty little object pool to avoid angering the memory manager. Then we want to ask the transform to apply this mathematical translation using our position object. And it needs to be converted to a float. Position y to float. So now we're translating on the x and y axis to this position. And finally, we simply submit that transform to our entity, and the entity takes it and draws the bitmap with it. Whew, okay. You can look at that while I rebuild and see if we get this in order. So matrix transforms are super handy. They're used in all game engines. I don't really know the math because I'm not a mathematician at all, but I know you really want to use the post version of these operations. I believe so that the operations are performed in the correct order. What we can see now is that the entities have moved, but they haven't, right? They're at the same position in the world, but the camera is placed smack dab here. Or rather, it's looking into the world positioned at this position. And so half of the screen is now camera blank space and half of the screen is in the game world. If we wanted to, we could ask the camera to look at the player, but I don't really have access to the player because we only have 4 entities and it's not being specially maintained. So we might want to look at that in the next video. Let's just check the little thing we have here. update build visible set render. So